Hello again, and welcome to another installment of our videos for PIC microcontrollers and our tool series that we're going to be doing. Some of our different software tools that we'll be messing with. If you haven't seen the first video, I highly recommend checking it out. It's kind of an intro into the first tool that we're looking at, which is this one here, which is LTSPICE, which is a SPICE simulator. It gives you the ability to simulate your different circuit designs, circuit models, and things like that. What we'll be paying attention today to is some of the AC analysis of circuits. We did kind of some DC analysis, some basic setup and whatnot in the first video. This one we'll be looking at doing AC stuffs. So first off, what we're going to do is we're going to come up here to our symbol. We're going to grab a voltage source. So here we go. Let's grab a resistor by typing the letter R on the keyboard. The shortcut for a resistor. Then by pressing F3, I'm going to get my wire. And that's another thing, you can draw through stuff and it will go ahead and trim the wire out for you, so you don't actually have to go to here and then grab the next one and go on it. You can just go straight through it and see it trims that out for you. So just kind of a little shortcut thing if you're in a hurry. Okay, so what I want to do is we're going to pull some current through here. Let's say, we'll do 30 ohms. Let's say we'll pull some current through it. But what I want to do is I want to set this voltage source up for AC. Right now it's on, you can do DC and some series resistance if you're wanting to do kind of like a battery. But if we click on advanced, we get a bunch of different things. And it gives you a small signal AC analysis. Well, we want the whole waveform and everything. So what we're going to do is we're going to choose the sine, because AC is a sine wave. Now let's do I'm going to do just normal household voltages here in the United States, which for our household stuff is around 120 volts or 110, 115, somewhere around in there. I'm going to pick 120, but it's around 120 volt. This is a single phase voltage. So what we're going to do is there is no DC offset, or at least we hope there isn't. There might be in reality, but you can play with that if you want to. Basically, that moves the sine wave up and down. But right now we're going to stick with 0 DC offset. The amplitude, okay, now for those of you that don't know, if you were to actually plug a meter into the wall outlet, again, like I said, this is in United States outlets, European outlets and things like that will be different voltages. Will be like, I think 240 volt or 230, somewhere around in there will be those voltages, and those are single phase voltages too, but they're a little different. But for this example, we're going to do ones that are in the United States. You're looking at, if you plug a meter into a wall and you see 120 volt, you're actually seeing the RMS voltage, which RMS stands for root mean squared. Basically, it's the average voltage that is happening is what it's showing you. So actually, to get the amplitude of the signal, the actual peak value of the AC waveform, you have to do square root of 2 times that 120 volt times that RMS value to actually get the peak value. Now I'm not going to go into why that is and everything, because it's kind of a long explanation, but that's what you have to do. So remember your square root of 2, and on 120 volt, if you take square root of 2 times 120, you get about 169.7, somewhere around in there. That's what you'll get for your peak value. And I'll show you later, if you're wanting to do RMS values, you can actually have LTSPICE, you can put in to take out that square root of 2 by dividing it out later on if you want to see what your RMS values will be, which is kind of a cool little trick. I'll show you that here in a little bit. Our frequency here for the United States is 60. Like I said, European voltages and things might be like 230, 240 volt, and then but they'll be 50 hertz systems and things like that. But here, for this example, we're doing 60, so 60 hertz systems. We have no delays or anything. I'm not changing any phase angles or anything like that. This would be like if you're going to do 3-phase, which we may do towards the end of this. We'll do a 3-phase demonstration. Well, then you'll change this phi, the phi or phi or however you want to pronounce it. But basically, the angle on the voltage you'll have to change, because for 3-phase they're all 120 degrees away from each other, so you have to change that. But for right now, we're just doing a single phase voltage, so all you need is just the amplitude and the frequency. So we'll hit OK. So now we've got the sine, and now if we go ahead and click run, of course it's going to ask us for a time step. I don't know, get a couple of, we'll do 100 milliseconds. That'll be about good. Pretty much the period at least for, or at least 60 hertz, whatever is about 16 milliseconds, roughly somewhere around in there. And so, you know, you just gotta think about your sine wave and whatnot. You could do, you know, your 2 pi and figure out the frequency, and then remember that when you're dealing with AC waveforms, to go pass from frequency to time domain or time domain to frequency domain, it's 1 over whatever you're dealing with. So if you know what frequency you're running at, 60 hertz, you know, will give you 1 period, then 1 over 60 will give you the time period. So it's about 16. In fact, we could just do that real quick, just to prove it. Let's grab the calculator, good old calculator, except we don't want programmer, we want just standard scientific. If we do 1 divided by 60, we get about 16.6 milliseconds for our fundamental. So let's put that in, 16.67, let's say. M for milliseconds. Remember, even I could even type a capital M and it still is milli, it's not mega. You have to actually type in MEG for mega. So okay, so we get 16 milliseconds. Well, let's go ahead and jump right in here and grab the voltage. And there we go. We get 1 single cycle, you know, more or less. That's essentially, and so there you go. So that proves that that works. So if you do 1 over the frequency that you're wanting to look at, or something like that, then that will give you the time base for it. So if you're wanting to look at, you know, 2 times that, where it's you know, you're looking at 120 hertz, so you've got 1 over 120. That should be 2 cycles worth. So you've got, or actually I messed that up. I mean, if it's twice that, if you want to do twice it, so you can get 2 pieces of the waveform, it's going to be 2 times the 1 over 60. You know, basically, or you could just say it's 16 milliseconds times 2. But if you want to keep it in the frequency deal, you'd have 2 over 60. And that's going to be 33.3 seconds. So if we want to take and go to our edit our simulation, we can say 33.3 milliseconds, and that should get us close to a couple cycles of the sine wave. And it does. You get 1 and 2. So that's one way to do it. Now, so far as for measuring, before we just had a DC line, so it was the same everywhere. If we click on our node name up here, we'll get our little box. And now, if you push your cursor over to it, you'll get this little 1, and that stands for the first set of axes, or cursor 1, that stands for the first cursor. And if you click and hold on it, I'm left clicking and holding on it, you can drag it around, and notice that the voltage corresponds to wherever you're at. So our peak was 169 is what we had, 169.7, somewhere around there. So here it is, 169 point something. I don't know if I'll get the 7 in there. I don't know. But anyway, let's see, you can measure the peak. And now, let's say you want to measure, you know, peak to peak or whatever, or yeah, you want to measure the difference somewhere or something like that. You know, you want to measure maybe the peak to peak timing or whatever. You can put one here, and then I think if you click on this again, you get the second cursor. I was just left clicking, or you can right click, and if you see here attached cursor, right now it's on first and second. You can choose whether to have no cursors, the first with the second, or display both of them. So either way you want to do it, click on this 2 times to get both cursors, or right click and choose it from that menu. Either way you want to do it. And then if you notice, cursor 2 now has a value, and I don't know, let's put it down here. Let's say we'll go 169, whatever. But put it down there. Now, if you go on down, you have difference of cursor 2 minus cursor 1. So it's going to take whatever values are here and subtract this one from it. So our difference, we've got, of course, since this one's negative or whatever, we've got, you know, negative 338.54 volts is what we got for that, you know. And then, of course, we run it up here. We should have close to 0, which, yeah, we got 23 millivolt, pretty much close to 0. They're basically subtracting because they're both equal. But another thing that would be helpful is let's say we wanted to know the timing between here and here, you know, and then there it is. It's about 16 milliseconds. So that's kind of 2 useful little tools to use, as these different little cursors, which are nice to have. And like again, okay, let's say I want to look at the current as well on here. So there's the current. What would be nice is if I could offset it a little bit. Let me take and put a capacitor in here. I'll put a capacitor in here or something. So I'm going to type C to bring a capacitor. We'll throw that in there. I don't know. We'll put I don't know, 1.5 micros or something. Hopefully that should make a phase difference. There we go. And that way I can move the current away from the voltage so I can demonstrate something real quick for you guys. What I wanted to show you is that let's get rid of both cursors. Let's just grab just one. Let's say we want to know what the current is at a certain voltage. So let's say, oh, I don't know, when the voltage is, I don't know, when this is peaked. Let's say when it's peaked. We'll come to one of the peaks, somewhere around there. Well, what's cool about this is that the cursor will stay where it is, and when you click on the current, it will just move down to wherever the current is. You notice that? So now you can see if you're looking at a certain voltage, you want to know what the current is there. You can plot both, and then it'll tell you exactly. So we got 2.38 milliamps at when the voltage is up here. Like I said, you click on the current, and it'll show you exactly what the current is at that point. So that's kind of a cool little trick that it'll do. So that's nice to have. So remember, you can do that too. So it's kind of a cool little tool. Alright, so I promised this video isn't going to be real long. I promised that we'd do a 3-phase one, so let's reconstruct, and we'll do a 3-phase one. We'll get rid of that. I'm going to kind of move things around a little bit. In fact, just delete all this. Okay. Now. Oh, and I don't think I showed you. I'm going to undo, which you can either go to Edit, Undo, or press F9. I know it's not Control Z. Don't ask me why. It just isn't. But I forgot to show you guys in the last video about the move and the drag command. If you go up here, there's a move and a drag command, F7 and F8. Okay. What the move command does when you have your fingers, see how one has fingers, one is kind of like a fist. The one with the fingers will just grab the component and move it. See, it'll break it away from the circuit and move it. See that? So it just breaks it away. Now, if you don't want it to break it away, you just want to move it, wires and all. That's where then you use the drag command. Then when you grab it, see how it moves the wires with it? So the drag command is a way to scoot stuff around without breaking the connection. So okay, so once again, we've got the move command that literally moves the component, and you've got the drag command that will drag it with the wires. Okay. So just wanted to show you guys that real quick. I'm going to take and hit F5 for my delete tool here, my little scissors, and I'm going to move. Let me use my move. I'm going to move some stuff around, and then I'm going to press F6, which is the copy or duplicate command, and I'm going to grab some others here. I need 3 of these. Okay, now I'm going to go back to my move, and we'll maybe see if we can't move some of this around so it somewhat makes sense. Somewhat see it. Okay, and I'm going to do a 3-phase Y connection. Oops, wrong button. Do a 3-phase Y connection. So in a Y connected system, everything is connected and grounded. All the negative sides are grounded. Okay, now our first one is going to be at 0, and we're going to have to change things around. Our peak for this, let's do, it's a 3-phase voltage. Let's do normal common industrial voltages, which are 208 is what we have here in the States, 208 60 hertz. So, and right off the top of my head, I don't remember what the square root of 2 times that or whatever is. So if we take 2 to the 1/2 power, which is basically square root of 2, times our 208, we get 294.156. So we need Oh wait, I'm sorry, I'm having a brain fart. It still is the 120. I apologize. I'm still in another mode. It's still 120. It's not square root of 2 times that. It's still, each one is 120, but phase to phase is 208. I'll show you that here in just a second. First off, we got 120 with 0 degrees, which is fine. That's the first one. Second one, we're now going to add a phase difference. We have 120 degrees difference. And then this one is another 120 degrees, so you can either do the 240 or you can do minus 120. You know, it's a circle, so either way you want to do it, you can do it. And then let's put some loads. Let's put some loads out here. We got 1, 2, 3 loads. Let's do a Y connected load. So get that one. Oops. And then we got our ground. Okay, we'll make this, I don't know, 10 ohms. We'll do a balanced load. 10 ohms and 10 ohms. Alright. That looks pretty good. So let's go ahead and hit our simulate. Now, what I was talking about before, where I don't know, I just had a brain fart there for a second, so excuse me. Each line will be, you know, our 169, or basically our peak voltage. And each line will be 120 degrees out of phase. So there, if those of you have played with three-phase signals stuff, that makes our three-phase waveform make sense. And so, like I said, all of them are peak values. Now, if let's say I want to add another graph, you can right-click and say Add Plot Plane, and it'll add another one. And now you got to make sure and click in which one you want to display in. So we want this one, so we're going to left-click once in there, come down to here, and let's say I want a phase-to-phase voltage. So there's phase-to-phase there. So if we click up here, move our cursor up here, and get up to the top. Yeah, we're going to have the 292 or whatever, which is the peak value of that, which is the the square root of 2 times 208. And to prove that, I'm going to show you how to alter these to where you can pull them to where their peak values are the RMS values. If you want, it's kind of a way of cheating. But you can right-click on this, and any equation you want to, you can type in here. So we can take this and say divided by SQRT, that stands for square root, or squirt, but square root, open parentheses, and we want the voltage, we want square root 2. Sorry, and then hit OK. Now we've got 207.5, or of course, depending on where my cursor is, it should be around, it's close to 208, I don't know if I can get exactly 208. It's probably going to be really fine. But anyway, basically you got 208 up here. And you can do the same thing down here. Like I said, if you've got, where are we at? Let's grab this and move this over here. You got 169 or whatever on this one. You could take this and divide it by QRT 2. Hit enter. And now it's about 120 volt. So that's one way to kind of cheat a little bit with taking your peak values and making them the RMS values by just dividing by square root of 2, if that's what you're looking for. Now, if you're actually doing, messing with the waveform or something, then you don't want to do that, because basically you're saying that the average is everywhere, and it's not. So anyway, well, that's kind of a quick rundown of how to play with AC, basically a type analysis using the transient analysis mode, and some different little tools and plot planes and things that you can do. What I'll probably do is this video, that's probably about it for this video. What I'm going to do for the next one is we'll probably start dealing with models and how to pull models, because LTSPICE, if you look in their deal, like, I don't know, type in LT anything, pretty much everything that linear technology makes is pretty much in here as a model, like all their different op amps and comparators and reference comparators, and pretty much just everything everything they have, even the LTC stuff, all their different drivers and all their cool stuff, they have models for in here. Well, what happens if you want, let's say, a Texas Instrument part or a non-semiconductor part or something like that? Well, that's not modeled in your little library here. Well, you have to import it in yourself and do it. And honestly, it seems like it'd be a lot of work to do that. It's really not. It's actually fairly straightforward. They even have a symbol generator that's part of this, that if you don't want to mess with trying to draw all the symbols and everything, it'll just draw a square. Now, it won't be the pretty, like if you download a MOSFET, let's say you download some sort of a transistor, and it doesn't have, and it's like a specialty one or something that maybe has a whole bunch of pins on it, maybe has like a 7-pin package or something like that, so you'd have to go in and modify like a N channel, let's say is what it is, an N channel schematic symbol to include those other all 7 of those pins. Well, if you don't want to have to mess with it, you can use the symbol generator, pull open the model file, and generate a symbol from it. Now, like I said, it won't generate the nice looking like MOSFET, the IEEE standard MOSFET symbol, but what it'll do is it'll generate a little box that has every pin labeled on it, and it depends on if the model labels them, gate, drain, source, or if the model just labels them pin 1, 2, 3. It depends, but whatever the model has labeled those pins, that's what will show up in the symbol generator. And so it'll be just a little box with all the information on it and all the pins and everything, and it's all ready to go, matches the model and everything. So that's kind of a slick feature. So we'll be looking at that kind of stuff. We'll be playing with how to import third-party models into LTSPICE and then manipulate and play with them. So stay tuned for that video. That'll be coming up. Hopefully you got some good information out of this one. And happy coding, happy building, and we'll see you next time. Thanks, guys.